Okay, good afternoon. This presentation is entitled The Economic Value of Environmental Data, a Notional Insurance Scheme for the European Anchovy. This work has been done by Paulina Lebontin, Adrian Lich, Javier Ruiz, John Manford, and me, Margarita, María, Rincón. This is a collaboration between Imperial College and National Spanish Research Council in the framework of the ECOKNOWS project. Okay, the main objective of the presentation is to compare the performance of two different harvest control rules for anchovy fishery in the Gulf of Cádiz. One adapting to and the other ignoring the effect of environment on recruitment. This is the Gulf of Cádiz, yeah? And it's a place where the environment highly affects the recruitment. And also, anchovy is a very important resource in Spain. It's the 5th most popular fish. And per capita consumption of anchovy was 2.7 kilograms in 2009. Knowing the importance of this, we are going to go to the plan. First, I'm going to explain how to simulate anchovy population dynamics driven by the environment in the Gulf of Cádiz. Then, how to simulate catches under a harvest control rule that uses environmental information. And then, how to simulate catches under a harvest control rule that ignores that environmental information. And finally, we are going to measure how both approaches goes with an insurance policy scheme. So first of all, I'm going to explain how the environment works in the Gulf of Cádiz. As anchovy spawning is mainly affected by temperature. It's associated to higher temperatures. And mortality from larvae to juveniles is mainly driven by extreme easterly winds. From juveniles to recruits, survival is mainly driven by discharges from the river, Guadalquivir River. And finally, when they are recruits or adults, the fishing pressure is the main cause of mortality. Okay. The Bayesian model that Javier explained in the morning is used here. The posteriors from this model is used here to make a forward projection model to simulate catches. With this model, we made 1,000 simulations for 360 months, 30 years, using the environment simulated from historical time series. And we noticed something. This is the effect of the joint effect of temperature and wind on survival. If the number of windy days during the first 2 months after spawning is less than 5, I know that many juveniles, many eggs have survived. And even though the effect of discharges of the river that is here is affecting very negative the population, you can see that most of the variance is explained by the wind and not by discharges. And if I'm going to propose a harvest control rule, I have to use this fact. And this is the thing that we did. The natural way F changes with the wind. As you can see, this is the same picture as you see before. And this is the harvest control rule with the same shape as the survival function. How it works. if the wind during the first 2 months is unfavorable, 4 months later, fishing pressure, if it is unfavorable, fishing pressure is going to be reduced. But if wind is favorable, 4 months later, fishing pressure is going to be increased. This is the first harvest control rule. The second harvest control rule is just to leave F constant. So we sample F from each simulation from posterior, but it is constant during the 360 months. With these two harvest control rules, we can now simulate catches with one harvest control rule and with the other one. And what happened? Here, the blue line is the median of the simulations under the environmental harvest control rule. And the black solid line is the median of the simulations under non-environmental harvest control rule. The dotted lines corresponds to percentiles 5 and 95. Also, the red lines are the maximum and minimum from historical records. So you can see that simulations are in the limits, and also that variability in the median with the environmental harvest control rule is less than with a non-environmental harvest control rule. Okay, now that we have all the catches simulated with a harvest control rule, but with the environmental harvest control rule, and with the non-environmental harvest control rule, we can compare using the insurance scheme to estimate the value of information. For all the simulations, we calculate the revenue just with the catches and a fixed price, and we calculate the insurance payments. Insurance company is going to pay when the revenue falls below 80% of the last 5 years average, and it is going to pay the difference. So we calculate revenue and insurance payment for all the simulations. And we sort them from the less one to the biggest one. The premium is defined to cover this 75%. The rest 25% is going to be covered by a reinsurance company. And now that we have premiums, reinsurance premiums, and revenues, we can answer this question: what it costs to insure the stock under the two harvest control rules. As you can see here, we have that with constant fishing mortality, we have a revenue of 200 million, and with the environmental harvest control rule, 210 millions. So at the beginning, it looks like you have a profit using the environmental harvest control rule. And also, if you see here, the insurance premium in both approaches and the reinsurance premium, it looks like we are saving money also in insurance payments. And finally, conclusions. Profits could be increased taking advantage of environmental information. You can see here the profit. Whoops. Cheaper to insure a fishery that operates under a harvest control rule which responds to environmental drivers. Here. And also this value, 4.1 million saved on insurance payment, represents the value of reducing variability and risk. This is the sum of this 3.1 million saved by the environmental harvest control rule plus this 1 million from the reinsurance premium. The question, is more complex management justified? It's in the air. We need to explore how robust the results are to alternative operating models and harvest control rules. So more investigation, more research is needed. And thank you very much.